The next thing is positron decay, which I already talked about a little bit. One of the interesting things about positrons is that when a positron is created, since it is an antiparticle, positrons don't really like to exist in our universe for any length of time. They interact very readily with matter, and when they do so, they actually undergo a process that's known as annihilation. So you start out with a particle that has some mass in it, and inevitably it's going to strike something that has electrons in it, and it's going to react with those electrons by annihilating it. So the process is going to look like this. We're going to start out with a positron, and it's going to react with an electron. And of course you see that these things are going to cancel one another out. So there's going to be, this is going to be 0 here, whatever that is. That's going to be 0. Turns out that it's going to actually produce a gamma. You're going to get a gamma emission. You actually get 2 gammas from this process, because each one produces a gamma. Each particle, as it is converted into from particle to energy, produces a gamma. And it's nice because each of the gammas are ejected 180 degrees. So these 2 particles came in here, this one came in here, and this one was going this way, and that one came in here and it was going the other way. They would annihilate, and these particles, this is the electron here, they would annihilate, and you get a gamma going this way and a gamma going that way. You can always tell when this is happening if you have the right kind of detector, because you can set a detector up in such a way that it does what's known as coincidence counting. And you can actually see simultaneously that you will detect 2 gammas that are really 180 degrees apart. So wherever they happen to be, and this is the way that the way that positron emission tomography, which we'll talk about later on, actually works, because it's actually producing these gammas, and these gammas are going to be produced in pairs in various directions, but they'll always be 180 degrees apart from one another. So if there's an extraneous gamma that doesn't have that 180 degree counterpart, it's not included in as part of the count. It's only when the detector senses both of those gammas simultaneously that you know that that's an annihilation event. And that's what happens during positron emission tomography. Okay, so you have the annihilation photons. You can actually calculate their energy. It turns out to be 1.022 million electron volts. It's 2 times the mass of the positron and the electron both have the same mass, 5.486 times 10 to the minus 4 mass units. 2 times that, times the 931.5 million electron volts per unit, gives us 1.022 million electron volts total, which means that the annihilation energy is going to be half of that, since there are 2 of them, and it's going to be 0.511 million electron volts. That will be the energy of each of the gammas that's being produced. Okay. All right, there's another example given on page 60. Let's see, what are we getting out of this? This particular example is actually showing positron emission. It is showing the decay of neon 18, and I'd like to actually just, again, all these calculations, and I don't want to, keep dwelling on these calculations. I'm not really going to give you these things on the exam anyway. At least if I did, I would provide you with all the formulas and everything. But there's, just to illustrate what's going on here, it's probably informative to look at page 61, which actually shows the decay of this neon isotope. And it's neon 18. and it's going to undergo positron decay, but it actually has multiple positron decays. So it's got one. In order to make the positron, remember we have to lose a little bit of energy. So it's got one that drops down here, and then we've got something that comes off here, and then we've got something that's lower energy, or actually greater energy transition. So we have a 2-point. Here we have a 2.38 million electron volt positron being produced here. And here we have a, what's the other one? It's 3.42. 3.42 million electron volt positron here. The difference between these two energies is that if we emit to this point, we still have to decay back down to the ground state. So in order to do that, the difference between these two is 1.04, so that's going to have to add up. It's 1.4 million electron volt, and that's going to be a gamma that's going to be emitted there. So that still gives you a net difference of 0. If you add up the lower energy positron plus its gamma will give you the energy of the higher energy positron. Okay, another process, electron capture, which we did talk about just very, very briefly. We're going to go into that in a little bit more detail now. And electron capture, in terms of what the shape of it, it looks a lot like positron decay, except you don't have the drop down that you have in the case of positron decay. So remember what's happening in the case of electron capture is that an orbital electron from the atom is actually being captured by the nucleus, and when that happens, a proton will convert into a neutron in the nucleus. So here's an example of this taking place. Well, first let's look at the general formula, which is given on page 61. So we're starting out with again with our x, and this is we're going to go from x, z, and a, and this time we're going to show, since this is a capture process, we're actually going to show the electron on this side of the equation, not on the other side of the equation. So we're going to put the electron on the left side, and that's going to give us y, which is now going to be z minus 1, and this will still be a. So this will be the process for electron capture, and still going to have to balance this with the emission of a neutrino. So we have the neutrino as well. But in general, the other way we could also write this, as the book points out, we could just write this as using this symbol, and then just put the arrow across and write EC for electron capture here, and then just show this part here. So an example is the isotope selenium-72. It decays via electron capture with a total energy of decay of 0.33 million electron volts. So again, you would show that over here. If you're going from here, it's the electron capture process goes to here. Then there is also an emission of a gamma, and the total difference, which is the total energy difference, which is what they just gave us, is 0.33 million electron volts. And we're going from selenium 72, and we can then just abbreviate this EC, electron capture, and then there's a gamma that's being produced, a 0.46 0.0460 MeV gamma. So we'd have to subtract that from this. Well, to find out how much, to find this energy difference, so that would be this part going to the first excited state would be the difference between those two, which would be about 0.29 MeV, and then that takes you down to arsenic 72 once you give off this gamma here. So that shows you the electron capture process. Your book also talks a little bit about the where these electrons are actually coming from. They tend to come mostly from the K shell, which is, if we go back and look at this according to the old Bohr model, you know, you've got first shell is K, and then there's another shell that's called L, and the other one is M. And these things roughly correspond to, when we talk about orbitals, we have S, P, and D orbitals. So there's only one S sublevel. There are three sublevels for P, so there are actually three L sublevels, which we could designate L sub 1, L sub 2, and L sub 3. And there's also, then there are going to be 5 M sublevels. So we have L sub 1, L sub 2, L sub 3, and M sub 1, M sub 2, M sub 3, M sub 4, and M sub 5. And we can actually designate the electron capture process by showing specifically which electron it is that's actually going to come crashing into the nucleus when this happens. But there's probabilities for these things. So about 90% of the time, actually there's only one K. I should have said that as well. So K has the greatest probability. Here's our nucleus in here. K has the greatest probability. Electrons from the K orbital are most likely, about 90% of the time, they'll come from the K orbital. About 9% of the time, they're going to come from the L orbital or one of the L suborbitals, and only 1% of the time will they originate from the M suborbitals. So we can actually that will give us some indication of the also of the relative energies of those particular transitions. So again, the K shell is very low in energy, much lower in energy than the transitions that would come from the L shell or the M shell. And in fact, where these other transitions might much more readily result in the emission of a gamma photon, the transitions where a K shell electron goes into the nucleus, being of lower energy, frequently will result in the emission of an X-ray rather than a gamma ray. And we call these continuous X-rays. I'm sorry, we call these, not continuous, I'm sorry, we call these characteristic X-rays. So characteristic, they're called characteristic X-rays because they have a particular energy that's associated with them. Whereas there are other kinds of X-rays that have a continuous spectrum, that is the energy could be any particular energy. These X-rays are actually quantized, which you would expect because there are specific energies for the electrons that are actually falling into the nucleus. They will always have quantized energies, so the X-rays that are going to be emitted will also be quantized. There's an example that your book is, which we'll talk about a little bit in more detail later on, is something called Bremsstrahlung. And Bremsstrahlung are, for instance, when an electron from another atom that just happens to be hurtling through space approaches the nucleus of this atom, it actually is slowed down somewhat. It's bent and slowed down, and when that slowing down process occurs, something called Bremsstrahlung. It's the German word which means braking radiation. It's actually because the nucleus causes this to break, like you're putting the brakes on. That energy has to be given off in some way, and it's given off in the form of X-rays. Now those are continuous X-rays rather than characteristic X-rays, Bremsstrahlung. So on page 64, they're showing you a K-shell electron falling into the nucleus. Well, originally you have a vacancy in the K-shell and a characteristic. So then you have what's actually happening is the K-shell. This is after electron capture has occurred. So there was an electron in the K-shell that already fell into the nucleus. Now there's a vacancy in the K-shell, and something from the L is going to have to fall into there. So we're going to get, depending on where it happens to originate, we're going to get a particular X-ray, and the X-rays are designated, have various kinds of designations. They might be designated as K sub alpha 1 or K sub alpha 2 or K sub beta 1. What that refers to is the alpha is telling us that this is going, the fact that it's K, it's telling us that it was the K electron that was actually lost in the electron capture process, and it's telling us that a K alpha 1 is telling us that something is falling from the L3 level to into the electron in the L3 suborbital is falling into the K shell, and a K alpha 2, the L2 is falling into the K shell. We'd expect there's also a K alpha 3, which would be the L1 electron falling into the K shell, and then there's a K prime beta 1, which is the M falling into the K shell. So these things, when this kind of thing happens, you have these associated characteristic X-rays that are actually produced. And in the case of this example, they're talking about holmium, which has 3 X-rays that are produced for those 3 transitions, the L3 to K, L2 to K, and M to K. It's 47.546 kiloelectron volts, 46.7 kiloelectron volts, and 53.91. Sometimes, though, instead of emitting the characteristic X-ray, there's another process that can occur. So this complicates things a little bit. So we can get this characteristic X-ray emission, or we can have something else happen. That energy has to go somewhere, has to be accounted for in some way. So rather than having the electron, say, if I produce a hole here, a vacancy here, rather than having this electron here fall into that hole, there's also the possibility that another electron, either this one or another electron, will actually get kicked out of the atom altogether, and in doing so, the energetics the energy will still balance out. So what we can have is we can have the ejection of an electron, and these electrons are known as Auger electrons, O-U-G-E-R, and the Auger electrons also have characteristic energies that are associated with them. And the Auger electrons are, they're actually going to be designated in a slightly different way. So rather than using the K alpha 1, K alpha 2, we'll use something like K L2, L3 when you see this kind of a designation rather than K sub alpha. This would tell you K sub alpha. Would have to be an X-ray. This kind of thing would tell you that this is an Auger electron. And this is telling us if we have an L2 to L3, it's telling us that the L2, the K shell had lost the electron, the Auger, rather than the L2 falling into the K had lost that. The L2 falls in and the L3 is ejected. So that's a K L2 L3 Auger electron. So all right. So again, L2 drops into the K shell and L3 is ejected. And that's Auger. The probability of X-ray production after electron capture is known as the fluorescent yield, and that's given by the symbol for that is omega, which is Greek letter omega. Looks a little bit like a sort of like a W, and that's called the fluorescent yield, and it's omega sub K in this case, the process actually increases with increasing Z number. So as the atomic number goes up, that probability of X-ray production after electron capture is going to increase. So we'd expect for increasing Z, X-ray increases. And for decreasing Z, we'd expect to see more Auger than X-ray. There also are what are known as multiple decay modes, and there are some isotopes, and there's one in particular, which is bromine 80, which undergoes these multiple decay modes. And this is an unusual isotope. It's not the only one that does this, but this is one of the more complicated kinds of decay diagrams in terms of what's actually taking place here. So this is actually shown on, oh, by the way, I just wanted to call to your attention on page 66, what I just talked about, the fluorescent yield as a function of atomic number. So the fluorescent yield, again, is the amount of X-rays that are being produced. And you can see that at very low atomic number, the fluorescent yield is essentially zero, probably at atomic numbers of up to about 5 or so. And then it gradually begins to pick up until it starts to approach 1, where you're getting almost 100% fluorescence and very little Auger electron expulsion. So, and that starts to happen up at atomic numbers of around maybe between 60 and 70, where it starts to plateau off. Maybe around 80 it starts to plateau off. So you can see that on page 66, this kind of a curve that looks like that. And this probably is about Z equals 80, and this would be, starts to pick up at about Z, maybe Z equals 5 or so, somewhere around there. And this is fluorescent yield going this way. So anyway, what I started to talk about before, bromine 80, very interesting isotope. It goes so we start out here, bromine 80, and we have multiple decay routes. So we have, first of all, we have some positronic decay routes. Let me just take a look at this for a second, because my eyes are not very good. Oh, I'm sorry, that's not, okay, I'm sorry. Okay, so first we have a decay, beta decay, that takes us to an excited state, which is eventually going to decay. So this is going to be an excited state of krypton. Krypton 80. And it's going to give off a 0.616 million electron volt gamma, and it will decay all the way down to krypton 80, stable krypton 80. And there's another possibility, which is positron decay. So we can undergo positron decay as well. And this is at a slightly higher energy level. That's going to take us down to selenium 80. So these are isobars. They all have the same mass number, 80, 80, 80, but they're different elements. These are isobars. So this particular isobar is at a lower energy than the selenium isobar, but nevertheless, bromine can undergo either decay to krypton 80 or to selenium 80, and there actually are two different mechanisms whereby it can undergo that decay. So it can get there in this process through positron decay. So it emits a positron that has an energy of looks like there are two positrons here. I'm having a little trouble seeing this, but oh, I'm sorry, no. This is the beta decay here. Because my eyes aren't that good, it's a little hard for me to read what's in the book. So in the beta decay, that's 2.00 MeV beta particle here. But the positron is 0.85 MeV for that positron. Or this can also decay by electron capture. So look at all these different routes. So this can also decay by electron capture. Takes us, so whether we do it by positron or electron capture, we still get to the same point. But you know, here we would, if we did it by electron capture, the overall difference is 1.87 million electron volts. So that's the entire process for that decay.